So he was. Thank you. So he was in sabbatical visiting Anasegeda, and well, we spent a couple of weeks together there, and then we saw that he already met many of you, Tobias, Ernesto, Horacio, and some others. So we have quite an overlap. So Luca is reader in complexity science in the Department of Engineering Mathematics in the University of Bristol. He did a PhD in New Mexico with Kenkre on transporting organic materials and biological systems. From there, he moved to work with Simon Levin in Bristol, and from there back to Bristol. Also, he's editor-in-chief in Movement Ecology, the journal. So he's really interested in movement, and well, I would say that his specialty is discrete, so doing calculations on discrete space, and movement is a part of it, and he has many papers on movement of birds and terrestrial animals. And he's currently running a program. It's a program at the Isaac Newton in Cambridge on mathematics, movement, and interdisciplinary approach to mutual challenges in animal ecology and cell biology. So you are interested, the program is running till the end of this year?
Yeah, it's not started. It's starting in a month. Okay. Or even a bit less than a month. Yeah.
Okay, but I mean, if you are interested, I mean, you can contact him, and I mean, for sure you will find some slot available there. And he's staying till tomorrow late in the afternoon, and probably he's sitting in my office up there. So feel free to write me or him, and we will find some time to talk. So thanks for coming, and well, the floor is yours.
Thanks, Victor, for the opportunity. I have to say, this is the first time I give this seminar to physicists, so I'm a bit scared, but hopefully it'll be all right. You know, I've always talked to biologists, and so, you know, I can hide lots of things, but, you know, now probably I cannot. So, yeah, so let me start by thanking the funding agency. And so Debras Das was a postdoc in my group, Dan and Toby are PhD students still in my group. Cyril and Sri, I mean, so-called Sri, he's just finished, you know, like 6 months ago. So he's now, I mean, in good, bigger pastures, I guess. So this is really the work that we have done over the 2 years, I guess, sort of. So what I'm going to tell you about, yeah, so I'm going to convince you that the convenience of using discrete versus continuous is because if you're interested in, you know, learning about interaction events, it's much easier than, you know, dealing with continuous, you know, so, and hopefully I convince you about that. So that's the main point of the talk. And I'll tell you specifically about reactive interactions. So, and, you know, in arbitrary number of targets. And so these examples are encounter and transmission events. So when you transmit some token of information, so binary, you know, object. And I'll tell you also about when there is disorder. So, and again, if you want, you have also multi-target, you know, encounter problem. But so how do you deal with disorder? How you can solve exactly all these problems as well? And so I'll give you an example of a continuous. So from discrete, you can actually do some limits, as you probably know. And then we found the new, you know, we just went beyond Smolkowski to just find the equation, a PDE for the presence of thin permeable barriers. So that was actually not known in the literature. So, and so it has many uses discrete. And I think I want to tell you what I'm super excited lately about hexagons. So we have solved the problem on hexagon and, you know, honeycomb lattices. This one, yeah, probably I won't have the time to about a little bit. So one step, no mark. You can also still push these techniques and then also study that, but I'm sure it skips various things. Okay, so what are the boundary value problems that you can think of in that context? So imagine that you have random walkers, and then you have typical situation. We have targets which are fixed. This is an exit problem. So it's at the boundary, you know. And so you ask the question. You might be interested in finding out how long it takes to get there. Another example, we have fixed targets. You're really searching for food or for whatever you're searching in your space. And again, instead of being at the outer shell, you know, it's actually sort of distributed anywhere. So this is a search problem. Now, a sort of a search problem again, if you're moving randomly, is that now you have a transmission problem. So there are lots of targets, and each of these locations you may or you may not pass something. No? So there is a probability of passing. So that's a classical encounter or transmission problem. And these are all reactive interactions. No? So the point that you compute something knowing that that's, the end of your, journey. Yeah? So that's, and so you don't preserve probability if you want. So here, and it's a problem that we have worked, we are actually still in review, but this is something where you have a heterogeneous space. And I give you some examples. So this is like a permeable barrier, as I mentioned earlier. So this is a poorly reflecting barrier. And this is a case where you actually go either faster compared to the rest or slower, no? So just the diffusivity is bigger or smaller, no? So this is what you should call them inert interaction, because essentially you preserve probability, and that's why you want to distinguish from the other one. The techniques to solve that problem is slightly different, but it's still a defect technique. And yeah, so that I told you about probability preserving, probability non-preserving. So these are the things that you'll hear me talking about. So now the main point why you can do in discrete, you can solve all of this because it's boundary value problem at specific sites. In this specific case, there are single sites. When you want to deal with this, you have to worry about between two sites, no? All of this, no? So that's what the fundamental trick is. So that's what I say there. And okay, so now why modeling is sorry, there was a question is why modeling movement with discrete variables? So who cares, no? But well, first let's answer for why the continuous variable being so successful, no? So, and I would say that somehow you can exploit symmetries, translation invariance is one that comes to my mind, or area symmetry, and then you can solve all these problems. Effectively, you reduce the PDE to a 1D problem, no? And so then you can solve it. So, and if essentially, so as I don't have to introduce the equation to you, so that's a classical example, and then all this problem with specific boundary condition which are known, which can be solved, Dirichlet, Neumann, radiation, and probably the one a bit less known, which is the permeable boundary condition. These are all problems that has been solved for that PDE in 1D. But what happens in higher dimension, it becomes a challenge to solve those problems in higher dimension. No? So fundamentally, you are losing all these symmetries, and then you have to do it numerically. No? So on the other hand, discrete, you can go forward and tackle the problem. So yeah, in discrete lattice, effectively you are perturbing the solution without your defects. So once you know the solution with the defects, you just perturb that, and you can find the solution analytically. And so all of these, as I told you, reactive and inert interaction are discrete boundary value problems. So you have a finite number of those. And yeah, I already told you this. And so now if you are convinced about this, so the question is that, well, do we know, this solution without the defects? And so that was probably what was not known before. And so once you know that, you can also sort of go in and follow all this procedure to find all the answer that you want. And so the point was that the starting point for all of this was indeed to try to solve that problem in higher dimension. No? So now the 1D case was sort of solved in different parts of the literature, in different contexts. And so what is now has to be, quantitative. So you have a random walker. It's discrete lattice, discrete time. You jump with some probability. You have some probability of staying, which is 1 minus q. Your q is your diffusivity, and you have a chance to move left or right q over 2. No? So that's your master equation, and you conserve probability, and then your boundaries you can sort of do all your boundaries. So you have reflecting boundaries. You just make sure that you have one specific look. You have the general equation, then you have two boundaries points that you have to worry about. And so the periodics are all the same. This one is your losing probability because it's an absorbing point. And this is a mix, you're losing probability on one side. No? So these are sort of known in the literature. And so what is the solution? So you'll see, I'll show you the solution because then you see what happens in higher dimension. So fundamentally, okay, this is a case for not the absorbing case. But what you have a spatial part, and you have a temporal part. So that's what they are. So then you have, and in this case, you see it's, your temporal part is very simple, no? So that's a 1D case for reflecting boundaries. So now what happens in higher dimension? Okay, let me just keep this one, but I want to show you. So now you start writing, you can write the equation in any dimension, no? And of course, where is the challenge here? Because in higher dimension, in discrete, in continuous, you do factorize. So this is exactly equal to that. But in discrete, it doesn't. So probably that was the reason why it were not solved. But this is a classic, in continuous, well known. No? So, but so why in discrete was not known? I don't know. So that was when all of this business started. So just to show you, so this is the first time I show you the derivation. I'm so happy about that. So they never allowed me before. So how do you actually go and solve it? Well, think about that you have that problem to solve, okay? So that's your master equation. I'm not rewriting, but you have seen it before. That's your master equation. And so what you have to do, you have to actually consider the problem is the unbounded problem, yeah? So just imagine now it's unbounded on this space. So you have a reflection here. So this is the case of the reflection. So now you solve that problem, yeah? And the way you solve it becomes a 1D because you Fourier transform, okay? So it's translation invariant along that axis. So you Fourier transform that. Now you can solve that problem because I show you the 1D case is solved, no? You just have parameters inside the equation which has K, no? So, so you do the generating function. So you transform that. I mean, sorry, you write the equation, you solve, you write the generating function, and then you actually find the solution of this in Z. Now, so there was the equation written in 1D, effective 1D. Then you write the solution of this problem in Z, N and K for the other axis. So, and then what you do, then you have to bound the space, no? So, well, you first inverse Fourier transform, yeah? Then you bound the space, yeah? And then you find your solution in Z, and then you invert from Z to time, and then you get your, and its solution is, I mean, Chebyshev polynomials and so on. Yeah, so that's, and then this is for 2D. Suppose you want 3D, no? Or whatever boundary condition combination, then you start with your known solution in 2D, then you have an axis here, which is your Fourier transform, and then you keep building up the solution. So that's the way you do it. Okay, so now once you have the solution, so what were we interested? So no, I have to show you, I mean, the specific case. This is the case where you have a reflecting box, 2D. I mean, it's a rectangle, and then you have a bias. So that's your equation. Oh, that's the equation without the bias. Now, suppose you want to put the bias, any bias. So now you modify, no? So now suddenly you start having this Q over 4 becomes your bias G1, which is that one of the axes. I mean, that axis, and this is the bias G2, which is that axis. And again, okay, it's a bit more complicated this case, but fundamentally the solution is always the same form. And sorry for I just want to show you that your spatial function is much more complicated because you have a bias, but the temporal part, as you can see here, is sort of similar to the 1D case, but it's, I mean, since it's 2D, you have a sum over R and sum over K, no? Yeah. And so that's where, you know, the fact that they don't, it's not a product of two 1D propagator. No? So this is the case. If you want, you can plot it. And then so this is a plot at a specific moment in time. You start here, it propagates, and then, you know, you sort of have this is reaching, the bias is sort of, where was the bias? Q1, G1, so yeah, so it sort of was a little bit component this way, that way, so that's why you see that now, for example. Okay, so now what do we do with all this knowledge? Now, well, we apply to the classical problem of first passage, for example. No? So now I don't know if I really need to go through this, probably. Let me skip this one because probably everybody knows about this in this environment. So all that you're interested to find out the first pass probability, the generating function, it's a ratio of the propagator. Now you can see, okay, what do you care about the propagators? That's what you need. You need this object, and that's what we have, and then you just plug it in and carry it through if you want. No? So that's what now, yeah. So, and if you want the mean time, you just, differentiate, and then you get your answer. So, and okay, you can also look about the case when you have more than one target. This was actually known. This results in two targets was actually, I think, well, not the full probability, but the mean time was known, and you can actually also look at that and find the answer. So that was the answer which was known. But what is actually more interesting is that when you have reactivity of target which is partial. So imagine it's not an actual fully absorbing point, but it can partial absorption. No? So then what's the general theory for that? And that was interesting because, it turns out that in the literature, if you think about, there are two regimes which are known. I mean, vaguely speaking, suppose that you have an encounter rate for a searcher to a target, and then you have a reaction rate once you're in proximity. So these are the two rates that are most interesting in the problem. So this is a widely used assumption that the sum of the rate gives you the actual rate of the combined process. And I don't know, was it eager to say it's not even wrong? So that's So there is only one case when it's right. Yeah, I'm going to show you. The rest is completely nonsensical. But so this is, this is. I mean, I know that Mathiesen's rules for some of you is known. So this is what is actually normally used, and the inverse addition knowing chemical reaction is also used. And so that's what it's been used. But now it's only valid in some extreme case that we know. So if you have the motion limited case, all that matters is a slow process, no? And so that's why your rate is actually only depending on, the slow process, no? So it takes a long time to get there. So, and the actual value, which is correct, is a reaction limited case. So then all that matters is V, no? So once you get, because you are always essentially there, you are so quick at moving if you want. So now there is also one more case that is true. So if this is the case when you have one target, yeah, and you have partial reactivity. So in that case, the structure is sort of the one that you see here, where you sum two objects. Now here you can compute exactly what that is, and you should not be surprised. What's that time there is a mean return time, no? So multiplied by this factor which has to do with the partial reactivity. Now if you have zero reactivity, so then of course you never get there, so you never get absorbed. And if rho is 1, it just becomes a mean first passage if you want. So that's the other case. But so how do you deal with when you have n targets? Yeah, so I don't think, I'd go through all the details, but for some of you, the Montreux defect techniques is well known. That's what you do. And essentially, let me just keep that. And so all that you need, which was not known before, is like to compute the splitting probability. So, because what you need is, suppose you have 3 targets, I need to know what's the probability of getting here and not these 2, then getting here and not these 2, and then getting there and not these 2. That gives the overall probability, no? Oh, and if you have m of them, it's the same thing. And so computing all of this permutation, that was not clear how to do it, no? But if you follow this technique, it comes out on its own. And so, so that's what you have. So if you have the first passage to any of these targets, irrespective, imagine you just have every time a single target, you're interested in finding out the first passage from one target to the other one, wherever they are. And so you make the ratio, the usual ratio, and then you get your first passage probability to those targets. And you need also to know if it's partial reaction, you need the return probability for that. And then you build the answer, which is, okay, so that's, so the answer is a sum of this ratio, this determinant. You can write it as a single determinant, don't worry, okay? But that's what you have. And inside here, these matrices, they do contain the individual first passage probability between different targets and between the initial condition and one target, with all the permutations. Okay? So in other words, you reduce the problem of a multi-target problem to an individual calculation of targets, position between targets and initial condition. So then you have your answer, and you can invert in time, the generating function to get in time the answer. So now just to show you, of course, that's a determinant. As soon as you open it up, it's like it blows up on you. But this is for 2 targets. And if you compute the mean first passage, so the mean transmission time in that case, and then you look at and you think about the previous, approximation, which is the sum of, of the inverse of quantities, and it's like it's nonsense, no? So, and so that's just to show you that we were really missing how to go about and computing this. Okay, so now let me show you that if you want to compute the mean time, it's a slightly simpler version of what you get, and then you have an expression which, okay, here I want to press upon you the fact that if you do simulation and you have 3 targets, this was a 4D square. I just decided to pick 4D square, and it's not that big, It's a 21 to the 4. And then simulation has not even converged after 10 to the 7, okay? So this is just to give you the power of this technique, okay? So, and there were 3 targets, and I think this, I was moving 1 target along 1 axis, So there were 3 targets, and so this is the mean first pattern, and the different values are different diffusivity. So this is the mean first passer to either of the 3 targets. I'm moving 1 coordinates or 1 target, just 1 coordinate of it because it's 4D. So actually, that reference for that figure is wrong, but anyway, so it's a different one. Now, just to be a bit more practical, since I like to be a bit more practical behind the theory, is that I give you an example of a predator-prey case. So you have a predator, which is starting from there. It has a bias to the corner. These are reflecting boundaries for the predator. This is a reflecting boundary for the prey. So the prey only stays inside here, starts there, and has a bias G1 there. No? Sorry, a bias G2, which has a relative angle theta. So, and now you can think about what's the probability of capture, which is a sort of first pass problem. But now there are many targets, no? It can be captured anywhere inside here. And then you have a partial reactivity because the capture can evade. So a parameter rho that you saw before I was talking about, no? So if you try to compute that, this is just the mean time, that expression I showed you, then you can see that, so rho equal 1, so it's perfectly efficient, the predator, to capture the prey. And when you go to rho, well, very highly inefficient, okay? And you can see from here to there, you swap the actual strategy that in principle the prey should follow. So if you want to, you sort of want to maximize the time it takes to be captured. I mean, you get captured at the end because it's a finite space, yeah, so there is no escape. But you like to be, here, perfect efficiency, you want theta equal 0, or pi, which is the same, no? Or, 2 pi is the same, which means that you want G2 to just go the corner because, this is coming in, and as soon as you are on the same site, you get captured, no? So that's what that is telling you, no? So you maximize, so it takes longer to be captured. Now, the opposite is the case when you go here because you go towards pi, you go towards the predator, not very clever. But if you go the other way around, it's the opposite, no? So what happens is that you go towards, here, 0, you go towards the predator, but then he may not catch you right away, no? And so what happens, you are in that corner, and this one is in that, eventually it picks you up, but that's why you have a swap, no? And then, and then you can compute how it goes about in between as you reduce the value of rho, no? And I forgot between these two, I've changed the diffusivity probably between these two. And this dotted here is an approximation because you can go to high order approximation instead of having to first order motion limited or first order reaction limited. So now, as you can see here, the units here, if you try to capture with a simulation this, you can just stay forever there, and then you can't really capture those features. So, okay, so now disease transmission, yeah. So now it's again, that's the same object you have to use. That's a full probability if you want. And the specific case is that if you consider it's anywhere you are, you pass infection with some probability rho, then it's, you don't need a vector rho, you just need a value rho. So you simplify a little bit, the expression is along the diagonal of those matrices, of that determinant there. So then you invert, the generating function, you get your time-dependent probability. And so this is what we did here. I think it was a 50 by 50, the size of the domain. And what you have here, you have two boundary conditions. You have a periodic, so they start at the corner. And you have a periodic boundary condition, and this is a reflecting boundary, same size. And so this one, you can see that, well, it's much quicker because at the boundary it means you're nearby. No? So of course, you have the maximum which is before, and then by the time they start meeting in the middle is when the reflecting comes in. That's the time scale of the reflecting probability of of transmission, which is exactly corresponds to when you have a plateauing, a slowing down of that. So that's, and then this is for perfect efficiency. And then if you put rho, which is smaller, then eventually you go to the regime, which is the reaction limited regime. Effectively becomes uniform here eventually for a long time. Until it's always exponential here tail because you're in a finite space. But so this is, and apparently this was, it was, but I haven't even seen simulation trying to do this. It's so that's something useful. So now just to show you, this one is the probability of transmission over any other location, no? But of course, it's made up of splitting probabilities. And so just to show you in a small domain, so this is like, I'm going to show you here the actual probability of transmissions of splitting at each of these locations. If you sum them up, you get this curve, no? Which is the one that you saw before on a bigger domain. And then you see, so they start at the corner. So this is a periodic one. And you will see that when it lights up, it's that, your probability is high, no? And then this one, you see nothing happens until eventually they start meeting here, which corresponds when you come here in time. No? So this is just a little video to show you that. So that's, you see, they start here, there is a chance of meeting, and then eventually they start spreading. And when you come here, then they start, this is the probability start to pick up there. And that's why there is a different peak values here because, but of course, it's all, probability is conserved. So eventually, has to do that. So if you want, given the COVID era, everybody knows what R0 is. And, I was surprised to see that nobody has ever computed in the context of the spatial explicit problem, no? So it's always about from, all sorts of, normal ODE equation or maybe simulations. Huh? So can we compute that? Yeah, we can. So because all you need is that, suppose that it's an SIR model, you have a probability of losing the infection. Suppose you have one infected person, a sea of susceptible in a given space. I forgot the domain that I've used here. And then you have a probability either of you go out of the system, the infected person, or you lose the infection. So you don't meet anybody before losing the infection. No? So, and you don't even have to invert anything to compute that because you just take the generating function at the 1 minus gamma. Huh? So that's it. So you compute those determinants, actually the single one, because you can write the single one, and that gives you that. And of course, it depends on the number of susceptible, no, that you have initially. It's all that matters that. Omega is the space that you're considering. And then you can play and change the value of gamma, and you get your curve, and these are simulation, okay. But and so you can see that you can actually obtain, a specific value. Now, of course, it's proportional on W, no? So that's why you have to divide by that. Okay, so this is, so I told you about reactive. Now we shift to inert interactions. So let's see. This is so just to give you an idea, I just want to show you, so an example of inert interaction. So you start with, your domain, which is, the one for which the propagator, and then you start modifying. So you might create area of exclusion, or you create barrier within. This is a fully reflecting barrier. And this is like, these are the sticky side that I call them. So because you slow down. No? And then you can also, you can also make some connection between long distance connection between 2 points or more than 2 points. No? So all you need to do is like, now your equation without these are all defects. No? These are pair defects. It's not single defects. These are pair defects. So once again, you start from what you know, which is the solution in these boxes, for example, in whatever dimension it might be. Then for all this pair, you sort of modify your transition probability. That's your defects. And I also show you here the case where in principle you put this long distance connection, but you modify, you see the A, these are the A are the original, you modify by this lambda, and then for preserving probability, that's why you have a summing over on this one. No? So you have to take some probability somewhere. No? So examples that I can show you is that this is the one, the long range connection. So your probability of staying gets used to actually connect it to, the long distance, for example. Or another example here, you have a sticky site. So this, pay attention to the thickness of this arrow. So you want to stay longer there. So you see that this is, is changing accordingly from this to that. And these are becoming thinner. So somewhere again, you lose probability and you gain somewhere else. No? So that's an example. So therefore, what happens as you do all this modification, you get your A prime. So you have a different transition tensor, okay, because it's in any dimension. No? So and so what you do is that so you start from that, and again, this is even more horrible algebra. But so your propagator with those defects is actually made out of this expression where you have this determinant, this matrix, it contains this paired propagator. No? In fact, just to impress you that you can actually do it. And what you see when you see this expression, these are the propagator which are paired, left and right, 2 sides. And these are the matrices that actually are in there. No? But again, so it's a slightly different version of the defect technique model, but it's a defect technique to derive those. And so you can compute, for example, then you can just, there is that. So now you can see, these are the starting point. And for example, in this case, I forgot, I think it was, 100 time steps. I mean, you need, you know, a split of a second to compute this, you know, it's just a determinant, no? And then, okay, with an integral because it's in Z, but, and as you see, there is this barrier that stops a little bit the spreading. And here you can see that since we're long range, it was starting here, and then this is a bit, you know, more yellow than other areas, no? That, you know, so, or, and you can see here, this one is because you stay longer there, that's a higher probability, no? Okay, so, yeah, let me skip this one. I just want to tell you an application of thigmotaxis. Probably, you know, there's animals that are like some insect that you put in a disc. They like to stay around the corners. I mean, the boundaries. Yeah? So this happens to be a circle. So this is actually a published paper by Miramontes and others. And these were termites. And you can see these are individual trajectories. And they are overimposed, and they always stay more there. So, sorry? Yeah, I mean, the cockroaches, no, sorry, these are termites. I think they need to know where they are, and so they use the antenna to stick to the boundary. So they sort of, as a reference for navigation, I think. But I have also an example here, a colleague of mine in Bristol, these are rats. Okay, they're much bigger. The arena is 1 meter. But, and see, these are different rats, different experiments. You see, they also, there, I think it's a different reason. So I'm not sure what the reason is there in that case, but that's, and so this is sort of, it's called thigmotaxis. No? So now, so if you are interested in modeling something like this, so, and you know, you can use all this machinery because you don't have to make always rates which are symmetrical, no? So when you have inert interaction, you may have something that goes more this way than that way. In as much as you conserve probability, that's not the problem, no? And so that's what you do now. So you think about the circle, you have an alpha in, you know, which is going to be different than, you know, the alpha out. So if you put a higher alpha out, then you're going to stick more on that side, no? So, and so in fact, you can do that. So, okay, let me just show you that. Indeed, this is the actual probability, which, okay, we haven't fit with the data, no, but this, just to show you that as you do that, so then that's your probability over time, and then this is a steady state, that's what happens, okay? Now, this is to impress you that, you know, it's starting from a discrete lattice, which was a square, and that's why you can see it's not perfectly a circle, but then you can actually, so in other words, you put lots of defects here, no? Okay. So anyway, okay, so now this I want to tell you because this is interesting. It's a bit less, you know, doing calculation, but I just a bit intuition. So now I give you the problem. And so far, every time I ask, nobody answers. Not even I was able to answer when I started. But so imagine I have a permeable barrier here, okay? And I start there, and I have to reach the target to the right, yeah? So, and I have a reflecting boundary here, and then I can move this permeable barrier, no? Yeah? So then if I ask you, does it take longer for the mean time to reach the target to the right if I closer with the permeable barrier to the starting point, or if I put it towards, you know, the reflecting boundary? The mean time. I mean, any intuition, I mean, you know, of course, if you have a permeable barrier, you may go through or not, no? I guess that once I said nobody answered, then everybody's scared. Yeah, so you either you have a probability of going through or not. Well, it depends what you put, no? But also in that case, pick 50%. And then we can change also that one. Just pick 50%. Yeah, I mean, you actually go through. No, it's not reflection. You actually, when you're there, you actually go through with a probability which is different than when it's not there. And so what that probability you modify, so 50% less, you know, than it's normal. Yeah. So, okay, so I give you the answer. Yeah. So, but okay, in this case, this is 1D, you can compute anything. And so your mean time is based on the mean time without the permeable barrier, plus the quantity, which depends. Do you remember this lambda I was telling you about? You modify this transition probability between pair of points. But now notice here, it may be 0 if U is to the left. So it doesn't change anything, okay? Wherever you put it. Yeah? So it remains a mean first passage to go from there to there as if there was no barrier. So it was a tricky question. When I was telling you, should it be close or not? Doesn't matter. It's irrelevant for the mean, not the probability. So, and then if you put it on the right, of course, it does matter, no? And in fact, they have a dependence there. So now I show you that the actual probability, if you actually plot it, so that's a mean. So that arrow is a mean. Now notice the probability is actually changing, no? And if you look at the color coding, so as I go to a smaller value, I'm getting closer to the barrier. So the yellow, you're closer to the barrier. And then, of course, when you're closer to the barrier, which is the yellow one, then, of course, lots of trajectory get reflected, no? So you have a higher effectively reflected, no? To go to the right. Therefore, your peak is higher, no? But then, also, the long time is there. It takes longer because if you actually go through, then you have lots of space to navigate and stay trapped inside. And that's why you have the high, longer tip. And then, of course, somehow you have to conserve probability. So that's why intermediate time is actually has this sort of funny shape. Yeah. So, and then if you actually put it to the right, as you can see, the mean is changing. No, I mean, these are the extreme values where the mean is changing. Okay, so this is something. Yeah. So I think I can tell you about the Smoluchowski. Yeah. So you can actually now think about putting a single barriers with discrete. And then again, you modify the equation and you actually try to, yeah, that's just to come back to what you're asking. So now instead of having a capital F, this is because it's continuous time. But anyway, you have a little f, no? This is an actual rate. I mean, you can do from discrete, but it's slightly smaller. It's symmetric, yeah. So then when you are R plus 1 to go to R or vice versa, it's smaller. Yeah. That's why, yeah. So then you can actually do the limit. And what you get your equation, which has now a J, which is a flux at the boundary, and with a delta prime, with a bigger delta. So, and instead of, if you want, this is the leather boundary condition, you have to solve this one plus the boundary condition. But now you have an actual equation there. Okay, I'm not going to go into details why it's much more convenient to have a single equation to write, and which accounts automatically for the leather boundary condition. Yeah. So, and this came from actually walking through the discrete. Yeah. So, and then of course you can generalize to Smoluchowski and so on. So, okay. So, now I'm going to tell you about the honeycomb. Yes, I think I have time. So I don't know if you've ever worked with hexagon. Quite an exciting system because now the axes are at 60 degrees one from one another. So it's not 90 degrees, no? So now, so essentially the way you create, imagine you have a cube and you slant it at 45 degrees. Yeah. And that's how you generate all those lattice points. So in other words, you can only move in principle, you can think about the walker in 3D, but actually only certain directions are allowed. No? So now, so that's how you generate. But actually, what is much more convenient to have this axis at 60 degrees from one another. And so the way you look at it is that the coordinates always satisfy this. You need, it's a 2D system, but it's much more convenient to think about the three axes and make sure that you always satisfy that. So, and so if you write the equation in that case, you just have to write your master equation, and you make sure that when you do this transition, in the hexagon, yeah, you see, I don't have I can't reach that, but so yeah, you can go in 6 directions, okay? So that's now the difference, and so in fact you have 6 terms here besides the one that you stay also. No? So that that one in unbounded space the solution was known, but now we were interested in the periodic case because we needed that to build the various finite domain solution. Now it was an interesting aspect to find out that, well, what do you mean by periodic in hexagons? Okay. Well, as you can see here, I just give you a simple example. This system is periodic, but also that system is periodic. It's exactly also periodic. And so what you have changed is that the way you have, I just rotate that from this way or that way, no? So that's why we call that left shift. So relative to this, which is the center, you can put that hexagon there, or you can put it one to the right. No? So that's why. So you have to decide and say what you have to do that. So, and then you build your, on your hexagon, you build your transition. And this is what you can see that can happen. And if you have the honeycomb, is the dual, no? And then you use that one, but then you have internal degrees of freedom. So it becomes a vectorial case. But then you can solve also that problem as well. No? So that has interest for, carbon nanotube and so on. So now, and then just to show you that you can, just to impress upon the solution, of course. Now, what's different is now this, as you can see, as you expect, probably, well, I'm not sure if you say you can expect. Now it's, they're not independent, the sum, no? So you see, now you're summing from S to M, and then this goes from M to the size of the hexagon, no? I mean, the overall hexagon. This is a periodic solution, and that's why at steady state, eventually you get 1 over the size of the domain, and it's quite more complicated this, but then you have, depending on which shift you have, which is this lambda index, you have your K depends on S or M in slightly different way, okay? So, but again, if you try to do the simulation, it's what, so then we just, we can use the analytics. And then what happens is that you can actually, what happens, you have reflecting boundaries, okay? Oh, the honeycomb is the vectorial one. I'm not even telling you about that. But now suppose that I have these scenarios, which is a reflecting case. So, and what I have to make sure that when I come here, I get reflected, no? And so I don't need the reflection point here, no? Because it's if I try, it's a periodic one underneath. So I come out and then just I get reflected. So you sort of minimize the number of these defects. But the way you build them up is, again, so you have to worry about 3 directions essentially, to build these defects, which are the reflection. And okay, so I think I have one plot. Indeed, I was telling you about the left and right shift may change. Yeah, so this has to do with the left or right shift. Yeah, this is telling you that if you are here, these are the direction where you can go, and look at the color here. This you can go there, there, or there, and the right shift, on the other hand, you can go here, here, or there. This is slightly different. Huh? So, but in as much as you are clear what you do, then there was the computation. You can show that you can clearly see a difference on the peak, when you do that. And okay, you can, of course, I mean, all the machinery I showed you before, you can port it over, and you can study multi-target and so on. So, yeah, so let me skip the application to the nanotube, but yeah, so I have the time to tell you about the correlation. Okay, so I'm lucky. So now what about, a little bit of no Markov, minimal effort, just one step, no Markov. So that's a correlated movement in space. Yeah, correlated in time, yeah. So now notice that I have a probability now at time t plus 2, and it depends on your t plus 1, and also you have a time dependence t. That's why 2 steps, no? So not just 1 step. So you can actually derive this equation by, as you know, the correlated is just, you can write Markov in a Markov wave as a vector, and then you can rewrite it like this. But sort of precisely exploiting the fact that it's a vector, you can carry through all these techniques, and you can actually show that you can find the solution in this case. And now, again, this is a reflecting barrier case, and you have a G which is the same as the 1D reflection, yeah. But now you see that your time dependence is way more complicated, no? But it has in it this, correlation coefficient, which is C, it's in there, and A is the probability of going forward, which is always, well, if you put 1/2 becomes diffusive case, but you can sort of carry through, and I'm not showing you the 2D is horrendous, but you can also do in 2D, but okay, so now, just to show you in 1D, so I mean, as a correlation, if you put the first step, which is equally likely left or right, you need to put you make a decision there, then you have 2 peaks, no? That's the Brodens, no? Like the standard continuous case variable. And that's what happens here, the Brodens and so on. And eventually your steady state is, uniform. Okay, so I think I'm there. So I've told you a bit about the one which is in red. I haven't told you about the others. Okay, thank you so much.
Oh, thanks, Luca, for very stimulating talk. Now, do you have time for questions?
Yeah.
In the problem of the predictor prey, I don't understand if also the predictor stays inside this reflecting region.
Not the small one, but the bigger one. He has reflecting domain on the bigger size, but not on the smaller one. So the smaller one is she doesn't see it.
Okay, so the prey actually is moving,
in the bigger space, but then is biases towards that corner, no?
Okay, and the second question is, I understand the shape of the first passage or the time or whatever.
You don't understand?
So, yeah, I understand very well. Because I have two maximum, I think, at 0 and then pi over 4.
Oh gosh, what happens here? Just a second. There you go. There. Wait. Yeah, so theta 0, theta.
Sorry, theta is the direction of the bias.
Yeah.
There. Okay.
Maybe I didn't explain correct. So theta is relative of the relative bias of the predator and with respect to G1, which is the prey. So when theta is 0, they are collinear.
Mm-hmm.
And so you are here, no? So this is theta 0, no?
Right, I have a maximum, yes.
So then if you are in the case where you're perfect, efficiency, then theta 0 means that you want to maximize the time you get captured, because you eventually get captured. So which is your mean time to get captured is maximized, if you have theta 0, because what happens comes this way, that one is at G2 equal G1. And so, well, it's going to capture, no? But at least if you go the other way around, which is theta pi, which is here, you minimize because you go towards the predator.
They cross each other and then they don't see each other.
Well, if rho is 1, they always see each other, unless it's those few cases that, depends on the value of G then, okay?
Okay.
So I forgot what value G we use here, but I think no, it's not written. But so it was maybe 0.5, 0.6, I don't remember. Yeah, of course, if you put G1 and then rho 1, then of course that's it. You die for sure.
And the two minimum pi over 2 it is.
So the two, I mean the pi. You mean this one? No, this one is. I mean, it's hard to explain. You have to go from here to there, no? Somehow. Yeah, of course. In the way to go, of course, you can actually go like this without developing those two bottom wells or not. I don't have an explanation precisely.
Okay.
I know because they still have a bias, so it's. You mean what do you mean, dear Tony?
Pi half. Pi half means that you are doing like that, so you are traveling.
Yeah, pi half means you're like this.
Yes.
Yeah, because that's.
Spiral. As the predator follows.
So pi over 2, they move parallel to each other.
Pi over 2 is like, these are the two. So this one is always coming there, and this one is there, no? So it's, what happens is that eventually you are going to be either stuck here or stuck there, in principle, no?
Mm.
So, yeah, why you have this? Again, I'm not completely sure. Maybe you have a better suggestion. But yeah, it's constant bias. No. Yeah, these are still random, completely random. So yeah. Yeah, so it's just. Yeah. No, yeah. So these are, it's discrete. So it's, it's unit is whatever you want to put it there, but it's number of steps. That's the first passage or first capture time. Yeah. It's. Oh, you're talking about the absolute value. Yeah. So it's no, but that's a capture time. So it is okay. Let me think. Yeah, no, you're right. Good point. So what happened is that somehow they have to even out. So there is a situation where they're sort of very canny. But yeah, you're right. So it's somehow it's lower than the actual absolute value there. Yeah.
Strange.
Yeah, strange.
Yeah.
Good point. Strange. Yeah. I have to recheck those numbers now that you're telling me. Yeah, it's Brownian with some bias. No, at the moment, no, no. I know it's dissatisfying, but we'll do it. We'll do it. I mean, no. There is a Weierstrass work, which is a discrete version, no? And how much we can do with the Weierstrass work, I can't tell you. I know we have plans to do it, but you know, it's. I think in discrete, I mean, as you put in periodic domain, you can do it. The Weierstrass work. I mean, because you wrap around, so you have an expression you can use. I don't know what, you know, what are the mathematical or computational implications as you start plotting things. So that I don't know. Yeah. Like that.